This is section 3.3, stoichiometry and chemical reactions. In this section we're going to look at three things. We're going to look at chemical reactions and equations, that is how we show what is reacting and what gets made after the reaction occurs. We're going to look at what the term balancing equation means, what balanced equations do and why. And then we're going to do the practical portion of this, which is reaction stoichiometry, which is mass-to-mass relationships involving chemical reactions. We've done mass relationships for chemical compounds, and now we're going to go on and look at chemical reactions. So the first thing is to look at how we write chemical reactions. When a chemical reaction occurs, the things that are reacting, that is the initial things that you start with, are called reactants. And we write those on the left. And then we use an arrow, and that arrow means a reaction happens. So a reaction occurs. And the things you make, the things that are formed after the reaction, or they're formed by the reaction, they're present after the reaction, are called the products. And so always the reactants are on the left and the products are on the right. And the arrow in the middle means a reaction occurs, and it's called a reaction arrow. Looking at one using molecular formulas, expanded shapes, this is the molecule propene. This is the molecule hydrogen chloride. They react and make this molecule, which is called 2-propane. And so these are the reactants. These two molecules react, and they form this one molecule. In fact, these two molecules here add together to form that product molecule. And this reaction is called an addition reaction. So we can write out in expanded formulas. You can also just write them out in regular chemical formulas, and it means the same thing. So we need to not confuse the chemical equation with what would happen if you were actually watching the reaction. So the chemical equation is really just a before and after. It's the initial and final states. It's not how you get there. So it would be like saying traveling from New York City to San Diego. You just know about New York City and you'd know San Diego, but you wouldn't know how you got there. You wouldn't know whether you flew, you wouldn't know whether you drove, you didn't know what cities you go through. It's basically just where you start, where you end. A mechanism is the pathway by how you get there. And so for this reaction, you start with these two molecules, you make this molecule. The way it happens is actually done in two steps, and we'll look at a little animation of that first. So you start with HCl and the propene. In the first step, the HCl reacts, the HCl breaks apart, and the hydrogen adds onto that carbon. Let's go back a second and look at that. So the HCl, this hydrogen, is going to add onto this carbon, leaving the chlorine with a negative charge. So that's the first step. The second step is that chlorine, that chloride ion, is then going to react with this positively charged carbon atom here. It's going to form a new bond there. So that's the second step. Oh, get to the end. So the final product is there. But the reaction occurred in two steps. So what we do is for the mechanism, we say it's a two-step mechanism. Step one is these react to make these things, which are called intermediates. And then the intermediates react in a second step here to make the final products. The mechanism does not play a role in chemical stoichiometry, so we're not going to be dealing with it now, but I just wanted you to know that the reaction equation does not tell you about how the reaction happens. It just tells you what's formed. We'll be looking at mechanisms in Chapter 14, or maybe Chapter 15 in next semester. Okay. Here's the most important thing about when you write chemical reactions. These things here are not different things than you have here. That is, the reactants don't go away and the products appear. What happens is the reactants rearrange themselves to form the products. These atoms are these atoms. They're the same atoms. So this chlorine is that chlorine. This hydrogen is that hydrogen. This carbon is that carbon. And so what's happening during the reaction is you're just rearranging how the molecules or how the atoms are bonded together. They're shuffling their connections, but you're not making new atoms and you're not getting rid of new atoms. Let's go back and look at our animation one more time. So when we start here, we have HCl and we have our propene. And so watch when the reaction happens, nothing is formed, no atoms appear or go away. They just move around. They just change what they're connected to. And that overall idea, the idea that no atoms are being created, no atoms being destroyed, is the law of conservation of matter. No atoms are produced during the reaction, no atoms are lost during the reaction. It's the same atoms. So because of that, what happens is the atoms here have to be the same atoms here. And that's in a moment what we'll do, what will drive us balancing our chemical equation. I want to draw out another reaction that's similar to the one we just looked at. This is the molecule acetylene, which is used, you might know, in torches, because it burns very, very well. So you can actually burn it underwater if you can light it. And that goes to make ethane. If it reacts with two hydrogen molecules, two H2 molecules. And so this reaction involves one of these and two of these. When you write that as a chemical equation, you indicate that there's one of the acetylenes by putting no number in front of it. And so when there's no number in a chemical reaction, it really means there's a 1 there. If there's a 1, you just don't write it. Similar to in a chemical formula. Because there are two hydrogen molecules, two H2 molecules, you write that 2 there. Because there are two of those, you put a 2 preceding the H2 molecule. And because there's a single ethane molecule, you put a 1 in front of it. Those numbers that are in front of the chemical formulas are called stoichiometric coefficients. They're coefficients for each molecule that's in the equation. Okay, so now let's look at balancing chemical equations. The idea, because of the conservation of matter, is you need the same number of atoms of each element on each side. That is, the atoms on the left side have to be the same as the atoms on the right side. The rule is that you can change the stoichiometric coefficients, you can change the numbers out here, but you can't change what is in what the formulas are. You can't change that. You can't change that. And you can't change that. You can't change that. You just change how many of them are present, either in the reactants or the products. And so what you do is you just go ahead and start. It's actually mostly done by trial and error. Sometimes there are some rules that make it a little easier, but basically you just kind of look at things and try to decide what you need to do. So I'll start with, on this one, with hydrogen, for example. I notice that here I have on my left side, I have 4 hydrogens. On my right side, I have only 2 hydrogens. So I need more hydrogens on the right side because I need the same number on both sides. The only place I have hydrogens on the right side is water. So what I'll do is, to get 4 hydrogens on that side, I'll put a 2 here. I can't change that 2 to a 4. That's not allowed. I'm only allowed to change how many of the waters there are. So I put a 2 there. So now I have 4 hydrogens on both sides. So hydrogen is balanced. Now let's balance the carbons. The carbon's actually already balanced. I have 1 carbon here, and I have 1 carbon here. So carbons just happen to be balanced, just coincidentally. Okay, so carbon and hydrogen are balanced, and we need to balance all of the atoms, all of the elements. And so the last thing to balance are the oxygens. So if we look on the right side now, we have a total of 4 oxygen atoms. There are 2 oxygen atoms in 1 CO2, and there are 2 oxygen atoms in 2 H2Os, because there's 1 oxygen in each H2O, and there are 2 of them. So we have 4 oxygen atoms here. We currently have only 2 oxygen atoms on the left side, because there's a single O2, but we need 4, so the way to get 4 oxygens on the left side is to put a 2 there. So what we can do then is we think we're done, and I'll write a 1 here now, but you generally would not. But just for this initial case, I'm going to erase some of this stuff so that we have more room, so we can check our balancing to make sure we're okay. And you should always, when you're balancing an equation, you should always do this. You don't have to write it out, but you should at least look at it and analyze it to make sure it's okay. And so what you do is you're just going to add up. We're going to add up how many atoms of each element on each side. So on the left, we have 1 carbon, we have 4 hydrogens, and we have 4 oxygens. On the right side, we have 1 carbon, we have 4 hydrogens, well, all those in the water, and we also have 4 oxygens, 2 in the CO2 and 2 in the water. So because those are there, it's balanced. That's the idea. Let's do a couple more examples. Let's do Mg and O2 react to make MgO. So the way you do this is when you look at it, you start with something and you try to decide what you need to change. So the Mg's are already balanced, because there's 1 of each on each side, so that's fine. But you need to balance the oxygens. There's 2 oxygens here, only 1 here. So the way to balance that is you need more oxygens on the right side, and so you'll put a 2 in front of that, so now that there are 2 oxygens on each side. Now the oxygens are balanced. There's 2 here and there's 2 here. But now the magnesiums are not balanced. You misbalance, you unbalance the magnesium while balancing the oxygen. So we now have 2 magnesiums on the left, and we solve that. I'm sorry, we have 2 magnesiums on the right, and we solve that by putting a 2 in front of the magnesium on the left. And now we have 2 magnesiums and 2 oxygens. And here we have 2 magnesiums and 2 oxygens. So that's balanced. Let's look at a slightly harder example. This is similar to our methane example. This is actually butane, like a butane lighter, like a cigarette lighter. So let's go ahead and balance the carbons first. There are 4 carbons on the left, 1 on the right, so we'll put a 4 there. So we've balanced 4 carbons. Now let's look at the hydrogens. When you're balancing these hydrocarbon things, it's these combustion reactions where things react with oxygen, it's easiest to carbon, hydrogen, and oxygen. You don't need to, but it's faster. Let's balance hydrogen. There are 10 hydrogens here. So each water has 2 hydrogens, so we'll need a 5 there. So carbon's balanced and hydrogen's balanced. Now we have to balance the oxygens. We have a total here of 8 oxygens from the CO2s, plus 5 oxygens from the H2Os, so that's a total of 13 oxygens. The problem is we can't get 13 oxygens there. To get 13 oxygens there, you would need 13 halves O2. That is, you would need 6.5 O2s to get 13 oxygen atoms. You're not allowed to have non-integer numbers as your stoichiometric coefficients because those are integers, because they have to be integers because they're representing numbers of molecules. You can't have half a molecule. So go ahead and write the 13.5 for now, 13 halves for now, or if you prefer, 6.5. So if you have 6.5 there, which gives us 13 oxygen atoms, so that part's okay. So it's balanced in that sense, but it's illegal, if you will. The way to get it balanced officially would be to double everything, to get rid of the half sign. And so you have to double everything. So you essentially what you do is you multiply the entire equation by 2. So you take that entire equation and multiply it by 2. And what you end up with is 2C4H10 plus, it'll now be 13 O2s, goes to make 8 CO2s plus 10 H2Os. So that should be balanced. Let's check it out. We have 8 carbons, we have 20 hydrogens, and we have 26 oxygens. Here we have 8 carbons, we have 20 carbons, we have 20 hydrogens. Those are all in the water because you have 10 waters. And for oxygens, you've got 16 here and 10 there, so you have 26 oxygens. So it is, in fact, balanced. The last thing you need to look for when you're balancing an equation is to not have, you have to have the smallest coefficients possible. So if you had 4 H2s plus 2 O2s go to make 4 H2Os, that would not be, that's balanced in terms of the numbers of atoms, but it's not balanced because you have to use the smallest numbers. So you would need to make that a 2, make that a 1, and make that a 2. So see if you can reduce it down to smaller integers when you can. Usually it'll be dividing by 2 step to do that. All right, here's a big misconception about balanced equations. The idea is the balanced equation is telling you how much reactants and how much products are formed. These numbers, the 1 here, the 2 here, and the 1 here and the 2 here, are not how much actually reacts and forms, except under very, very specific rare occasions. What it's telling you instead is it's telling you the ratio of molecules reacting. And therefore, because numbers of molecules is proportional to the number of moles, it's actually telling you the ratio of moles reacting and forming. And so the balanced equation becomes essentially our key to relating how much of one thing is reacting or forming to all the others. That is, if you know any one of these things, if you know how much of it reacts and forms in terms of moles, you'll know how much of all the other ones are reacting or forming in moles, because the balanced equation tells us the relative numbers reacting and forming. So because of that, the balanced equation is a new conversion factor. It's a mole-to-mole conversion factor for that reaction, for the reaction that you're looking at. And so we have this balanced equation here. There's 1 mole of that, there's 1 mole of that. And so you can write a whole lot of equalities for this and then write out conversion factors. So 1 mole of CH4 equals 2 moles of O2 for purposes of this reaction. And 1 mole of CH4 also equals 1 mole of CO2. And 1 mole of CH4 also equals 2 moles of H2O in terms of the amount of chemical change occurring in this reaction. And so you can do that with any of these connections. You can do it from anywhere to anywhere else. So you can say 2 moles of H2O equals 1 mole of CO2. That is, you can connect this to that. And so any of the relationships that are possible between these you can use. And because of that, you can use any of these equalities to make conversion factors. So during the reaction, you can say 2 moles, using this one here, you can say 2 moles of H2O react per 1 mole, or are formed per 1 mole of CH4. Or, if you need to, you can use it upside down. 1 mole of CH4 is reacting for every 2 moles of H2O formed. So what you'll do is you'll use these stoichiometric coefficients in pairs, any pair you like, to make stoichiometric factors. And the factors will be able to relate moles of one thing to moles of the other things. Okay, so let's look at the way this works, and we're going to use we're going to start building what's called an amounts table. We're going to do a simple one now. We'll do more complicated ones later on. For this reaction, it's 0.46 moles of O2 react, how much CO2 and H2O are formed, and how much CH4 reacts in terms of moles. And so for this, what you do is, I'm going to put my ones here for now, our amount of O2 reacting is 0.46. So the change in O2 is minus 0.46 moles. And that's because we know 0.46 moles are reacting, so it's going to go away because it's reacting. Okay, so let's look at CH4. What you can do is you can say 0.46 moles of O2 minus 0.46 moles of O2. That's a change of that. And you can make your relationship between O2 and CH4 by saying 1 mole of CH4 is involved for every 2 moles of O2. So therefore, you have minus 0.23 moles of CH4. That is, that's the change in CH4. So it's minus 0.23. Now you could just do that in your head because you know that this O2 is reacting 0.46 moles, and you know for every 1 CH4, 2 O2s react, or for every 2 O2s, only 1 CH4 reacts. Half as much CH4 reacts as O2. So the amount of CH4 decrease should be half that of the O2 decrease. The amount of O2 lost equals the amount of H2O gained, because you have 2 moles of O2 reacting to form 2 moles of H2O. So that's going to be plus 0.46 moles. The amount of CO2 forming, I'll write that one out. So you have, I won't write out. For every 2 moles of O2 reacting, you make 1 mole of CO2. So if you have 0.46 moles of O2 reacting, you have 0.23 moles of CO2 forming. These are positive because they're forming. And I would recommend when you do any of these calculations, don't even worry about the signs. Just calculate how much, and you always know that the reactants are going to be negatives and the products are always going to be positives. Because these are reacting, so they're going away. And so for any particular reaction, if you know how much any one of these is changing, you'll know how much all the other ones are changing in terms of moles. The last part of this is to go and look at what happens in real experiments. In real experiments, you don't weigh moles. There isn't a balance that weighs moles. There are balances that weigh grams. And so what we're really doing is we're looking at the mass that's involved in a reaction, not moles. And so what we're now going to look at is gram-to-gram conversions as opposed to mole-to-mole conversions we just did. And the path for this involves multiple steps. The moles to moles portion of this that we just looked at uses the balanced equation. The balanced equation is our key, our conversion factor to get from moles of one species to moles of another species. To get from grams of one, these A's and B's are like molecule A and molecule B, two different molecules involved in the reaction, either reactants or products. To get from the grams of A to moles of B, for that use the molar mass of A. So we've done that before, earlier. So the molar mass of A gets you from grams of A to moles of A. Once you know the moles of A, you can figure out how many moles of B. You use the balanced equation for that. Once you know the moles of B, you can figure out the grams of that using the molar mass of B. So you have three steps. You have steps a step going from grams of one thing to its moles. That uses the molar mass. A second step is going from moles of one thing to moles of another thing. That's the new thing we're introducing here. Uses the balanced equation. And going from moles of that second thing to grams of it is using the molar mass, which we've done before. So let's look at an example. We'll use our same CH4 example. If 25 grams of O2 react, what mass of CH4 reacts, and what masses of CO2 and H2O are formed? So what I usually do when I have these is I point to what I know and write down what it is. So I know I have 25.0 grams of that. And let's just do the CH4 to start. I'm looking for how much of that I have. So I'll put a question mark and grams. So I'm looking for how many grams of that. That just kind of, as I'm looking at it, gives me a key to what I'm doing. So the steps are going to be grams of O2 will be converted to give us moles of O2. That's the first step. Second step, moles of O2 will be converted to give us moles of CH4. And then the last step, moles of CH4, will be used to give us grams of CH4, which I miswrote. So those are the steps we'll use. So the first step is easy enough, 25.0 grams times 1 mole of O2 over 16.0. Oh, nope, it's O2, so it's 32 grams, 32.00 grams. So I have 25 divided by 32. That calculator's not working. The question when you're making these things is, should I edit that out, or should I just make you listen to me look for a calculator? I think you just have to listen to me look for a calculator, which I found. So that's 0.78. And when I start out, I just write down like 4 significant figures. It's more than you have, but 0.78125. I'll do 5 of them. So that's that many moles of O2. 0.78125 moles of O2. That's 25 grams of O2. Now, 0.78125 moles of O2 I can use to convert to moles of CH4. And I do that by the fact that there's 2 O2s for every 1 CH4 reacting. So there's 1 mole of CH4 reacting for every 2 moles of O2 reacting. And that's what the stoichiometric coefficients in the balanced equation are for. So that gives me 0.03906. 0.3903906 moles of CH4 that have reacted. And finally, I can convert that to 0.03906 moles of CH4 to grams using its molar mass. Now notice the molar mass will be different now, because earlier I had the molar mass for O2. Now I'm going to use the molar mass for CH4. And because I'm converting from moles to grams, 1 mole of CH4 is on the bottom. And the molar mass for CH4 is 16.04 grams of CH4. So I multiply that by 16.04. And that gives me 6.27. 6.27 grams of CH4. Now let's go ahead and do amount of CO2, for example. notice that I know that I had 0.03906, 0.3906 moles of that reacted. Therefore, because one CH4 makes one CO2, I know I make 0.3906 moles of CO2, because for every 1 mole of this that reacts, you make 1 mole of that. In addition, because I know the amount of O2 I used in moles was 0.78125, 0.78125 moles, because I used that many moles of O2, because every 2 moles of O2 make 2 moles of water, those numbers will be the same. So I know I make 0.78125 moles of water. And I'm not going to go through the math for it, but then you just convert that to grams of CO2, and you convert that to grams of water using their respective molar masses. And that's how this works. It's just that.